Okay, we were talking about soldering, and we talked about soldering and brazing are basically the same types of processes. They've been used for thousands of years, and the only way we differentiate them is by temperature. In fact, we don't always do that because silver soldering is actually brazing. But we call it silver soldering just because that's the jargon that people have come up with. And I also spent a fair amount of time talking about cleanliness of solder joints and the fact that they degrade rapidly over time. You grow surface oxides within minutes. Actually, we know you grow contamination films within microseconds and nanoseconds. The Langmuir is 10 to the minus 8 atmosphere seconds. You'll get a monolayer of surface contamination at 1 atmosphere pressure in 10 to the minus 8 seconds. Well, the oxide actually grows over several minutes, and in 10 or 15 minutes, it kind of reaches not a final state, but it will have grown significantly over that period of time. I showed you a little curve of some of that people have measured over time. But it continues to grow, and we're going to talk a little bit more about cleaning today so far as that goes. And then we talked about how you have to have spreadability and thermal stability, and finally got to acetic acid. And acetic acid is interesting in that it sort of dissolves. It's a flux that dissolves the oxide. Acetic acid has a certain solubility for copper oxide. It doesn't necessarily reduce it, but some fluxes operate by dissolving the contaminants. You actually, sometimes people, if they're soldering to, if you're soldering to gold or sometimes even copper, you can just use oil. And the contaminant there that you're dissolving is basically the greases. You got a hydrocarbon, it dissolves the, you know, if you actually look at the hierarchy of contamination on a surface, it's typically moisture, oils, oxides, and then you finally get down to the metal. The oxide grows very rapidly. The oils we mentioned the fact there's oils in the room. I mean, when someone perspires, they're kind of emitting oils. And if you could actually see yourself walking down the hallway with Tyndall lighting, which is this kind of lighting coming in from the side, it's just like looking at the sun coming in the window and you see the dust particles, and they look huge. Well, they're invisible. I mean, they're here in this air, and we're breathing it, but if the sun's not hitting it the right way, it doesn't reflect off of it. Well, if you saw yourself walking down the hallway with Tyndall lighting, you would look just like Pigpen and Peanuts. You know, there would be this big cloud of stuff around you. And in fact, that's what people have to worry about in clean rooms, okay? When you're making silicon or things like that, you have to worry about the fact that people are emitting all kinds of things all the time. The interesting thing is a lot of things that we produce as we're breathing and whatnot are carcinogens. I mean, there are methyl chloride and things like that that we actually produce in our body. But anyway, which are officially carcinogens. Obviously, they're not. There's got to be some low level at which the carcinogens are not harmful, but that's not the way the regulators deal with things. So you can dissolve the contaminants. You can reduce the contaminants. The example up here is acetic acid and copper oxide. The example here is typically if you use hydrogen gas as your flux, which we don't do that often in soldering because we have other fairly mild fluxes that aren't all that harmful. But we do in brazing. We use hydrogen quite often in brazing to reduce the oxides at the higher temperatures. And hydrogen reacts to form water vapor, right? And that reduces the metal oxide, whatever it is. In terms of reducing things, another example is to use chlorides. In that case, or amines in soldering. And that's what happens when you add a little bit of hydrochloric acid to that acetic acid. you now are getting something that eats away the copper oxide as well as it dissolves it, changes it to copper chloride. And the copper chloride is more readily dissolvable in the acetic acid, so it cleans it quite well. And the third thing, unfortunately, is called a reaction flux. And if you look at the little table that's in your handout that I put up yesterday, it talks about aluminum requires pre-coating for electronic applications and soldering. It says very difficult, or most difficult to solder is aluminum. Oops, I better zoom this down. Okay, but the aluminum and aluminum bronze, it basically says the most difficult to solder. Okay, and in fact, the way you solder aluminum is you use fluxes which contain tin chloride, which tin chloride is, or zinc chloride. And what happens with the reaction flux is you have the aluminum oxide, which is very tenacious. Aluminum oxide melts at 2,000 degrees centigrade. It's basically corundum as grinding wheels. It's sapphire if it's single crystal. In fact, did you know nowadays, you know, your watch faces now are typically sapphire? They're no longer quartz. Back in the old days, it was just glass and they get scratched up. They don't scratch up anymore, if you notice. If you know. But they're actually sapphire on a decent watch. I mean, there's a $100 Seiko or whatever. But on a decent watch, you go buy a Timex for $19, and no, it's not. It's still just a glass thing, and it'll get scratched against lots of things. Because glass scratches against, you know, hard steel can scratch it, but other minerals and things like that can scratch it. In a $100 watch now, it used to be in a $3,000 watch, they would give you a sapphire, what do they call it? It's not the bezel. The bezel is the thing that goes around. Crystal, yeah, the crystal. Actually, but it's now, even in a $100 watch, growing aluminum oxide has gotten to be so, single crystal aluminum oxide has gotten to be so inexpensive, and cutting it and everything else with diamond tools that, you know, in a $100 watch you can get a sapphire crystal. That wasn't true 15 years ago. Anyway, so you got aluminum oxide, which is very hard, very stable thermodynamically, and it will react with, you could write this down for the zinc chloride reaction, and I'm not going to balance this. Actually, I will. X, Y, and Z over here. It will form aluminum trichloride plus tin. Okay. And where's my oxygen go? Oh, wait a second. It'll form aluminum trichloride and tin. It's not really reacting with. Let me back up. It's not really reacting with the aluminum oxide. What it does is, if I've got this layer of aluminum oxide on the aluminum metal, as you heat things up, you actually form little fissures, and the flux will get down in here. I'm sorry, I wrote down the wrong reaction. Here we go. It's aluminum metal plus tin chloride forms aluminum chloride plus tin. And so there is a reaction here. You form tin, and down here is where the aluminum metal reacts with the tin chloride and forms aluminum chloride, and the tin precipitates out here, and you basically get a molten layer of tin that floats away the aluminum oxide. The aluminum oxide doesn't actually get reacted with or dissolved. There is a chemical reaction, but the chemical reaction is with the metallic aluminum. And it only takes, remember, 300 degrees to get a thermal expansion mismatch, typically, that's going to cause things to have little micro fissures. So I have this molten flux on top of the aluminum oxide. I heat things up, you get these little micro fissures. The tin chloride finds its way down those little micro fissures, gets down there to the aluminum. Aluminum trichloride at these temperatures goes off as a gas. So I start bubbling some gas under here, and I start forming a little tin layer, and I pre-tin my aluminum. And if I do it well, and also kind of scrub it ultrasonically or something, I can hopefully float away the aluminum oxide, just like, you know, icebergs off a glacier kind of being carried away by the ocean, right? So it's kind of a special thing that's not used very often. And in fact, the big problem with all of this is these tin chlorides and zinc chlorides tend to be very hygroscopic. In fact, they're so hygroscopic, they're called deliquescent. Anybody ever heard deliquescent before? Something is deliquescent if you took a crystal of tin chloride and put it on the table here, and you came back half an hour later, and I'm talking about something the size of a single grain of salt, you would find a drop of water about the size of well, probably a BB size, and if you came back 5 or 6 hours, it might be the size of half a small pea. The tin chlorides, some of the chlorides absorb water so readily that they actually will absorb many times their own weight in the moisture, and so they're called deliquescent in that case. It just means they're hygroscopic. They love to pick up water from the atmosphere. Of course, if they do that, it's no longer tin chloride. It becomes a tin chloride solution. But that tin chloride solution doesn't react the same way because now I got moisture around. And what happens if it turns out if I form aluminum chloride in the presence of moisture, I get aluminum oxide and hydrochloric acid. Okay, so, and that doesn't do much of anything. And so a little bit of moisture will screw up these fluxes. And so I've actually you can buy these fluxes commercially, and you basically can, in New England where we have lots of nice humidity, you can open it up. If you leave the little container of flux open on the table for more than an hour or two, it basically doesn't work anymore. I had someone from Florida once call me because they were doing this, you know, using these aluminum fluxes they had purchased, and they said, "We're having a lot of problem with consistency." I said, "Yeah. What do you have for humidity?" "Well, we have an air conditioner, but I mean, there's still enough humidity around. If you're in Arizona, maybe it works, okay? But you almost have to be in a very low humidity controlled environment to use these types of fluxes. But they are used. And unfortunately, they call it a reaction flux. This is also a reaction, okay? This is a reaction, but it's not a reaction with the contaminant. It's a reaction with the base material. And it turns out no one's ever found anything that would do the same thing with beryllium and titanium, and so they're basically unsolderable. In fact, they're not even very brazeable. Well, at very high temperatures they're brazeable, but not at the lower temperatures. Okay, so we have this problem of trying to evaluate whether the solder is going to flow across the surface. And remember, if I had brought in my printed circuit board, you've got thousands of connections, and one of them that's bad means a certain amount of rework. In fact, the whole rework problem in electronics is sort of an interesting story in itself. It turns out for many years, if you were building a printed circuit board line, the rule in the industry is you had to have a rework facility capacity to rework 4% of your product. Okay, you just expect that one board out of 25, when it goes through tests, is going to find that it doesn't work, and you have to go in there and do some manual repair. Well, it turns out about 15 years ago, when they were first, was it cell phones? Those pagers. I think it was pagers at a Motorola facility. They had a manager who was big on Six Sigma quality and things like that. And he says, when they were designing, it used to be when they designed the plant, they always designed for a certain amount of rework. And it was 4% was the rule. And the manager came in when they were designing this plant, and he says, "We're not going to design any rework facility. We're going to make it right the first time." And it turns out that was the first time they ever broke the 4% barrier. Because basically what happened is the engineers had to go out there and fine-tune the first time process to make it right enough that they got a low enough level of rejects, like 1 out of 100 or 1 out of 300, that they could just scrap the boards, okay, rather than rework them. I mean, if the reject rate is low enough, you can test them, and if they fail, you just throw them away. It's not worth reworking them. If it's 4%, you can't throw away 4% of your components and everything. I mean, you on a printed circuit board, your cost, material cost, might be 97% of your total circuit board cost. Just all the electrical components, the labor and everything's almost nothing. So you got to get it down to a pretty low level. And so that was one of the first times people realized that they were designing in their repair rate. What they were willing to accept ended up becoming their repair rate. Because essentially the engineers in a plant, if they had a 4% rework capacity, they would fix, if the rework got backing up, they would go and they would fix whatever was causing the rework problem. And once they got to the point where the rework facility could handle the product, they'd stop fixing that and they'd go off to some other problem, right? But when they had no rework facility, they had to fix the original problem, and therefore they actually drove down below the barrier. So it was the person who designed the layout of the plant that was determining the rework for the printed circuit boards. And that principle actually applies in other cases. It turns out there was a manager at Ford on a Mustang plant in Detroit. And typically, they assemble all the vehicles, fill them up with gas, and at the end of the assembly line, they get in, they turn the key, and the thing's supposed to start up, and the guy drives it out into the parking lot, and eventually it's going to be loaded onto the railroad cars or the trucks or whatever and taken to the dealerships and whatnot. Well, it turns out there's a certain number of vehicles at the end of the assembly line that when you turn that key, it doesn't start. And so they used to have a little tow motor vehicle or whatever, and they'd pull it out into a rework area out in the parking lot, and then mechanics would come by and they would fix them so that they would start. Of course, you never knew if you got the one that was the one that didn't work. Well, anyway, so this one manager decided, no, we're not going to have that. He says, we're not going to have any tow motors. If it doesn't start when you turn it on the end of the assembly line, you got to push it out by hand. And within a month or two, all those guys at the end of the assembly line who were in the same union as the other guys are, basically, or whether they were in the same union as the maintenance guys, they basically beat up on the engineers and the maintenance people to fix them so that they worked. Because when they turned that key on, they didn't want to have to push that vehicle 100 or 200 yards out into the parking lot. And so, again, it was, if you give people enough incentive, they will actually fix the problem and make it right the first time. Now, that was an important lesson learned in the early 90s at Ford, and it was carried over to a couple of other plants. And what I've heard recently is they've just gone back to the old ways. So, as they had cutbacks in engineering staff and maintenance and stuff, they got more and more rework, and the guys were spending all their time just pushing it out. And so the manager, to solve the problem, just created a rework facility, right? So now they have to rework the cars, and they don't always start when they at the end of the assembly line. So it doesn't matter whether you're making printed circuit boards or whether you're assembling automobiles. This is kind of the same principle. Okay. So in the soldering business, you have to have ways to determine whether you've got good solder joints. So it turns out there are various ways or good solderability. So one of these tests is called the dip test. And this is a very, very, I told you before, there's not a lot of quantitative stuff to soldering. There actually is some good science and research that's been done, so we understand a fair amount about soldering. But it's such a complex process, it's hard to really put good numbers on it. But for quality control, people are trying to get some quantification. And so the dip test is, well, the simplest dip test is you basically just take a copper wire and you take a hot plate with some flux on top of some molten solder, and you dip the wire in there and you pull it up and you say, well, did it tin or not? Okay, did it get any solder on it when you pick it up? Is it silver color or is it still copper color? Well, they get more sophisticated. They actually build machines that dip it for a given controlled amount of time. Okay, so you know exactly what's happening. And they basically see cam for 5-second dwell time in the solder bath. Okay, so you're not relying on variability of human error and stuff in how long they do it. But that's one type of test. Another test is what they call the rotary dip test. I don't remember if I got a picture of that in one of these things. The rotary dip test. So, let's see. Okay. There's the automated dip test schematic. The rotary dip test is nothing more than you take this printed circuit board and you put it on an arm, and you have a drive mechanism, and basically you swing it through, just like a pendulum. So you got a solder, you got a bigger solder bath, and actually the way you solder a printed circuit board typically is you have a big bath of solder in this machine, and actually you'll pump the solder up over a weir, so it's just solder flowing over a little dam, and so you have the solder coming over this little dam, and you bring your circuit board up in there, and as it passes over the dam, it gets coated with solder on the backside, right? So it's a nice continuous line. It's all in a controlled atmosphere, or you sometimes have fluxes which are nothing but a foam. It looks like firefighter's foam on top of the liquid solder bath, and you have this solder bath of 2,000 pounds of solder, molten solder, in this tank that's being pumped over this little dam, and circuit boards come through, and they got this foam flux. It's basically an aqueous zinc chloride or something solution, or a rosin solution or whatever, that fluxes the solder board as it's going over, and you hopefully get every one of your joints soldered. And there are problems because nowadays we have circuit boards where they're using both sides of the circuit board. We've all seen circuit boards where they just use one side, and you see all your components on one side, and you look on the back side, and all you see is the little wires that stick through, and that they only solder from one side. Well, nowadays they're trying to cram more and more. They talk about the real estate on the circuit board, and so they will solder one side. Well, actually, they'll there's various ways they do it. Sometimes they will solder one side of the circuit board with the components with one particular melting point of solder, and then they will put the components on the other side, and then they will pass it through another at a lower melting point solder, so they don't melt the first ones. So it basically goes through and gets both sides. In other cases, what's most common nowadays is they use what they call surface mount technology, and they basically use an adhesive to glue the component onto the board. And they have automatic robots that put the little capacitors and resistors and semiconductor chips at different points on the board, and they might use, they use those kind of gull wing things we talked about before. Remember I showed you pictures of the J-lead connectors and the gull wing connectors, which are, you just got a little chip package, and it's got these little metal connectors coming out, and a whole array of them around here. You glue it on the board, and then you pass that through the solder bath, okay? Or nowadays, even more common than that, you actually screen print on the solder board before you put the stuff down a solder powder or solder paste. And basically, you take very fine solder powder, lead tin solder, as a very fine powder, and you mix it with something like Vaseline. It's not all that much more sophisticated than Vaseline, although it might have some fluxing constituents in it. And you screen print it on, just like you were screen printing a t-shirt, onto the solder board, and then you put your components down with some adhesive, and then you don't have a solder bath with this weir. You don't have to add any extra solder. It's already there as the paste, and you put it through an infrared furnace, and the infrared furnace heats everything up and melts it, hopefully. And so you've made your circuit board that way. Well, in something like, in the old thing where you have a weir and you're passing the thing through, you would just, in order to control things, you'd have a controlled arm, and you'd sweep the thing through, and you can control the time at which the circuit board sits there. One of the problems is if you have to control the time, because if the electrical components all sat there at the solder bath temperature, at that type of temperature for a long period of time, they may start to degrade. You have to have long enough time to get the solder to flow, but not so much time that the components degrade. In fact, I gave you a problem like that if you do the problem set. The problem, as I worked it out, or as the students first worked it out, doesn't have a solution. It turns out the minimum speed is greater than the maximum speed. If you have a maximum speed, which is the time it takes, you can't go faster than it takes to get the solder to wet, and you have a minimum speed, you can't go so slow that you end up burning up your electrical components. It turns out that I actually just kind of threw some typical numbers in, and I came up with a situation where there is no acceptable speed, okay? You don't get solder wetting because of the numbers I used. But that's the way the real world works sometimes, so I never corrected the problem. Okay, so there's the dip test, just for a simple wire. There's the rotary dip, where you put a whole circuit board. There's another thing where they basically just take a piece of solder, a wire, and a mandrel, and they just heat the whole thing up, and afterwards they see if everything flowed together, and you can put flux on there or whatever. And then you get fancy, and for $50,000 you can buy a little tabletop machine that basically is an instrumented solder dip wire test. And it doesn't show everything, but it's got controlled crosshead movement, and the thing comes down and it weighs. There's a transducer in here, so you're actually going to measure the force on the wire as it goes in, and you will get a curve that looks something like this, where this is the wire that you wanted, the copper or whatever that you freshly cleaned, hopefully, and you're going to push it in. As soon as it hits the surface, there's nothing that happens. There's no wetting. Initially, as it tries to go beneath the molten solder surface, it's not wetted, and so therefore surface tension is creating a contact angle that actually is making it float. And so the weight of this thing actually decreases. And the further you push it in, the lower the weight, the more it's floating. You're basically just taking a rubber ball, a balloon, and pushing it under the water, if you will, in this case under the molten lead tin solder. It'll get to a point here at the neutral point where it starts to wet, but it's not complete wetting, and the contact angle goes back to 0, and now the weight will go back to 0, or to its original weight. And then you get up here where it actually starts to wet, and actually will start to suck it into the solder. And so you'll get a negative force, and when you pull it out, you actually get the thing kind of grabbing on here. And so you actually get an instrumented curve. And you can talk about the times between these points. You can talk about the slopes of the curves. You can talk about, you got parameters now that you don't know what to do with. And that's basically what they do with them, nothing. You've got so much information now that, but it's all empirical information. So those are the types of tests that people do. I dug up a couple of other things here. We talked about spreading. You need to have spreadability of the solder. And these are different solder alloy families in terms of what they call the spread ratio. The spread ratio, you just take a little ball of solder and you put it onto whatever substrate, if it's copper or nickel or whatever you're soldering to. And then you heat it up and you see how far it spreads out. Starts out at 1 diameter as a ball and it spreads out to a pancake. What's the diameter of the pancake? And what time? So here they're going to measure, and excess temperature is the temperature above the melting point. And as you go to higher and higher temperatures, the things will flow better. Now, there's been a tremendous push. Millions and tens of millions of dollars, if not hundreds of millions around the world, have been spent in the last 10 or 15 years to get the lead out of the solder. In fact, the first place where people got the lead out of the solder is in water piping for potable water in your house. Okay, one of the #1 criteria for waterworks in the United States today is to reduce the lead levels in the water, because you don't want all your children to grow up stupid like you. Okay? Now, and I don't know what we're going to say about all the British back in England in the 1800s when they actually used lead piping. Okay? They were one of the first countries. They were kind of the most sophisticated country in the 1800s, and they started having indoor plumbing. And they didn't use copper, they used lead. And you go over to some old British mansions and stuff, and they still have some lead pipes. In fact, my house, which was built in 1933 when I first moved in 25 years ago, actually had a lead pipe in the basement. It wasn't part of the incoming pipe, it was actually an exit pipe. But lead has excellent corrosion resistance. I mean, I think, is the roof of Kresge? No, the roof of Kresge, I think at one time was lead, but anyway. But lead is often used for roofing and things, has excellent atmospheric and water corrosion resistance.
Still has some lead piping. It's actually like 1920s house. It still has the piping from the street going in. It's lead.
It's lead, yeah. And is that the potable water system?
Yeah.
See? Just raising a batch of, mentally deficient people. Mentally challenged, right? Okay. I mean.
I like thinking myself as special.
Okay. So, oh, you are special. And in fact, I don't know. I never ate lead paint as a kid, not that I remember. But apparently it has a sweet flavor, and that's why children eat the lead paint off walls and stuff. Okay.
And you call our country crazy?
It's just, hey, there were lead pipes in my house in the 1930s, so your mother's house in the 1920s. I mean, the point is, these things still exist in spots. But nowadays in the United States, they want to, I don't remember, once a year I get something with my water bill that tells me what their level of lead content is, and you're down to the parts per, they're down in the parts per billion, I think, because they're controlling the water chemistry to keep the lead low. Well, and as they do that, they're not controlling the, they used to control the water chemistry to control the corrosion of the water coming into your house. Now they're trying to control the lead, which is not the same as trying to reduce the corrosion. And so there are cases that I know of where they got water pipes forming sprinkler systems in the building, but the lead's low, you know. So you can't control everything. But in any case, people are trying to get the lead out of solders, and they've spent hundreds of millions of dollars over the last 10 to 15 years because the environmental agencies keep lowering the lead content. There's a situation of a gold mine in Canada where the incoming water, actually it's arsenic, not lead, but the natural arsenic in this river in the wilds of Alaska is like 7 parts per million arsenic. And so they use that water for the gold mining operation, and the EPA requires them to have less than 1 part per million arsenic in their water that they put back into the river. So they actually have to clean it up and then dirty it up by just putting it in with the rest of the river water again. But those are the rules, you know. It makes no sense, and there's a tremendous cost when they're mining gold, so the cost is all factored in there. But it's sort of silly to do that. People don't realize what some of the natural causes are. But in any case, we're trying to replace lead tin, and if you look at the tin alloys, look how easy, with almost no increase in temperature, okay, excess temperature of 25 degrees Fahrenheit, you can get lead tin flowing and spreading out wonderfully. But if you go to tin silver alloys, which are some of the things that people have been replacing, and certainly what people have replaced in the plumbing systems, okay, they've started using tin silver alloys. I think it's 95 tin, 5 silver, and the plumbers hate it. In the old days, the plumbers used to plumb up, you know, some part of a building and have 100 joints, and they'd have, you know, 1 leak out of 3 jobs. So they might get 1 leaking when they pressure tested it or leak tested it. They'd have, you know, one part in 300 as leaks. Now they can do 100 joints on a job, and they can expect 5 or 6 leaks. Okay, and it. Tin's not carcinogenic. Tin actually is added as a supplement. If you go to the health food store where they sell all these extra vitamins you don't need, you'll actually see that they'll sell you tin. Okay, so it's a supplement to your diet. So, you know, I used to run clam bakes for the people at church and things. And I had these galvanized tubs, and someone came up once, and they were all concerned because they heard that the galvanized has some lead in it, and the lead would be leaching out into the water, and so supposedly that would be getting into the corn or the lobsters or the clams or whatever. And it turns out they don't understand. Yes, there is a little bit of lead. It's down in the parts per million regime. But if you get like 1/10 of a percent lead in your zinc, it embrittles it. It all goes to the grain boundary and it destroys the properties. So I said, no, there's not a lot, you know. I mean, but there is some lead and zinc. They both come from the same ores, and there's always going to be some impurity. But it's very, very low. But no, they were all concerned about whether they could eat something out of the galvanized that had been boiled in a galvanized pot. That's right. Did you know oysters contain more than 1% zinc? Oysters tend to concentrate the zinc. And same thing, if you go to a food supplement store, you'll find bottles of zinc, you know, tablets of zinc, and you eat zinc, okay? So I actually did explain that to them. I said, oh, you know, it's no worse than eating oysters, right? You get zinc. But they were concerned about whether it was leaching the lead out. Of course, then I get people worrying about leaching chromium out of the stainless steel cookware, you know, or nickel. There's nickel in stainless steel cookware. lo and behold, you know, just think of all these things in our environment that are killing us. And we all die eventually. It's true, you know. But anyway. Nonetheless, lead, there is nothing better than lead tin in terms of spreadability. And you can look at all these different things. This is the silver system. Here's the bismuth system, the indium system. And they're all significantly worse than lead tin. There's a reason why we've always used lead tin for soldering. It is absolutely the best. And actually, one of the problems with the tin, not the lead tin so much, but the lead tin alloy will actually stay in the joint. It actually acts as this, it flows extremely well, but it also will fill up the joint and not flow out of the joint. It tends to act like it has a higher viscosity. I'm not saying it has a higher viscosity, but it stays in the joint. The surface tension or whatever is such, and I'm not sure people really understand this. But tin is an alloy, if it's mostly tin without the lead, that just flows extremely well. It flows better than water. And so it'll flow out of the joint. That's one of the reasons the plumbers, if they have a very narrow temperature range where they can get a complete joint. They either don't heat it enough and they don't get enough flow and they end up with an incomplete joint in the pipe, or they heat it too much and it flows out of the joint, leaving a gap. So that's why their defect rate is probably going up by 50 to 100. And so it causes them frustration. They like to take pride in their work, although I guess they get extra work, or it takes longer to do everything. So far as cleaning things, I have various plots, but this one basically shows average contamination as sodium chloride equivalent micrograms. Okay, it's just a way of measuring. If I'm trying to clean something, if I reflow the solder, it turns out it's still fairly contaminated on the surface. It's still got all the junk that flows to the surface that was in the solder paste or whatever. If I clean it in water, I can get down pretty low. Water plus ultrasonic is pretty low. If I clean it in alcohol, I get the greases off, but I don't get quite as low as just the water cleaning. Alcohol plus ultrasonic is basically the same as the water cleaning. Semi-aqueous, which I'm not sure what that is, I'd have to read the thing, doesn't do as well. So there are various ways to try to clean things. To give you something quantitative, comes out of this same soldering book. If I don't do anything, the remaining contaminants on the surface in grams per square inch are 35 milligrams per square inch. Typically, if I dissolve it in a solvent like alcohol, I can drop that by a factor of 10. If I spray it, and the problem with immersion is you put it in, but the grease kind of floats on the surface of that solvent. And when you pull it out, some of it comes, you're pulling it out through this film of grease. And so by spraying it on, you basically get rid of that problem. You just wash it off. You get a little bit lower. And so vapor degreasing is the best, spraying and then vapor degreasing. Spray and vapor, you're down to 3% of what you had originally. And ultrasonic will get you down even lower. And the reason is some of your contaminants are just dust particles. And as the particles get smaller and smaller, they actually adhere to the surface by electrostatic charges. And I don't know that actually I do have that. It's actually the next page in this thing. It's a little table that basically says that if the particle is 1 centimeter in diameter, it's basically gravitational force is the weight holding the particle on the surface. If it's 5 millimeters, there's 100 times the gravitational force. I don't know where they're getting all these things, but in any case, and we're going to actually go through the equation later here in a little bit. Actually, maybe I'll go ahead and do it now. That talks about the relative surface tension forces versus gravity forces that are holding things onto a surface. Contaminants, solid contaminants, little particle contaminants on a surface. I just have to find my notes for that. Okay. So one way to think of this, if I got a particle and I want to know, you can try to solve it as there's a little bit of moisture that holds that particle as an adhesion mechanism, or if I just want to know if I've got a particle and whether it's going to form a nice perfect sphere, or whether it's going to slump on the surface. Okay, it can slump depending on how it wets, but it's going to slump and form some sort of shape, some somewhat triangular circle, if you will. Okay, because it's going to slump under gravity. What's the ratio of surface tension forces to gravity forces? Here it's surface tension down here. Here it's surface tension of the particle trying to make it a sphere versus the gravity forces trying to pancake it. And it turns out there's a dimensionless number called the bond number, and that's someone's name. It has nothing to do with bonding per se. But the surface tension force, the force on this particle trying to make it a sphere, is 2 gamma over r. It's gamma times the curvature we talked about before. And in this case, for a sphere, the curvature is 1 over r plus 1 over r. It's the 2 principal radii of curvature, and for a sphere, the 2 principal radii are both equal, because the radius in both directions around the equator and around the poles is both r. So that's equal, if you will, to gamma 1 over r1 plus 1 over r2. And in this case, r1 and r2 are equal, so it's 2 gamma over r. That's the thing that wants to make soap bubbles spherical. That's the pressure that, or the force, the pressure force that wants to make a solder ball, a nice small solder ball. And then the gravity force here, if I have some average height, h, the gravity force, which is trying to pancake it, is rho gh. In this case, h, you can say, is almost equal to r. And the bond number is, if I can get this right, whether it's gravity to surface tension or reverse. My notes give it to me properly. The bond number is the, I think it's surface tension. This may be 1 over the bond number. Anyway, I may have it reversed, but I think I got it right. To the gravity force. You're going to, like any good dimensionless number, you're just taking, in this case, you're taking these 2 forces, and that's 2 gamma over r times 1 over rho g h, but I'm going to change that h to r, and I'm going to end up with 2 gamma rho g r squared. So approximately the bond number for a solder ball or something like that is 2 rho g, let's see, 2 gamma over rho g r squared. Now if I put in typical numbers for a metal into that equation, I'm going to find that the bond number is 1 when the radius is about 0.5 millimeters, or the diameter is equal to 1 millimeter. It depends on what numbers you put in, but I don't know if I actually did I run the numbers once. So typical value for a surface tension of a solder might be 1 joule per centimeter squared. So if gamma is equal to 1 joule per meter squared, per meter squared, and rho is about 10 grams per cubic centimeters. So anyway, this is 1,000 dynes per centimeter. Gravity is 980. And if you solve all that, actually, if you solve that particular one, you get R is 3 millimeters rather than half a millimeter. But anyway, so that basically, well, okay. I should have looked at it before. So let's change this to 3 millimeters and 6 millimeters, if you will. It could be, if you're talking other metals with higher surface tensions or lower densities and whatnot. But if you have something that unfortunately, okay, I think I've run into this problem before. This paper is very high quality paper in this guy. Okay. Here we have some solder balls with wires going through, and they put different amounts of solder on there. And you'd like to get a nice kind of fillet that looks like this or this. Okay, nice kind of cone. Here I don't have enough solder, but over here you actually start to see this thing start to slump. And so the distance across here is probably a couple of millimeters. You're actually starting to see there is still a gravity effect. Even if the bond number is a tenth, which would be 1 millimeter, if R is 1 millimeter, the bond number would be about a tenth because it goes as R squared. And so, so far as that goes. So if I've got something a couple of millimeters across, then gravity has a 10% effect and the thing's going to slump like this to a certain extent. If I get much smaller than a millimeter, then everything's just going to naturally form a sphere. And I had a situation once when the guy, I guess I'm running out of time again, so I'll just tell one or two stories quickly. A guy came to me when I was a young assistant professor, and he wanted to make ruthenium balls, spherical balls for the tips of ballpoint pens. He was in the ball bearing business. And the only way he could buy ruthenium, which happens to be a hexagonal close packed metal, was as a powder, a very fine powder, but it wasn't big enough for these, okay? He couldn't buy a wire, and ordinarily when you make a ball like that, you basically just buy a wire and chop it up into right circular cylinders, and then you grind it down into a sphere between two flat grinding plates. And I said, well, I can do that for you. He says, well, how? Well, I took him across the road to the same electron beam unit that I had melted my wife's platinum iridium engagement ring, and I basically just took took some of the powder. I took a ball bearing and I whacked the piece of copper block with the ball bearing with a hammer and made a little somewhat spherical indentation, and we put some of the powder in there, and I put it in the vacuum system, and I put the electron beam over it, and I melted it. The copper had good thermal conductivity, so you don't melt the copper, and the ruthenium just balled up into a perfect little ball about a half a millimeter or a millimeter in size, which is exactly what he wanted. I said, all you have to do is melt it, and surface tension will, there might be a little bump on the bottom because of gravity, but it was a very, very small bump. And he could take those balls and he could put them between his plates, and he wanted it because ruthenium has excellent chloride resistance, and most of your inks have a lot of chlorides in them, and so he's going to try to make very, very expensive ballpoint pens for one of the pen manufacturers down here in Rhode Island. Ooh, who could that be? Same people who make these pens. In any case, and he says, well, okay, I need 10,000 of them. Oh, okay. So it was one of the first consulting jobs I ever, well, actually, I tried to do it myself. I made up a little grid with the 10 by 10 array on the copper, and I would put the powder on there, and I would just kind of run the electron beam by. And I would get like 90 balls every time. Well, this is pumping this thing down and everything. I said, this is not the right way to do this, because there's going to be 100 times in the vacuum chamber, over 100 times in the vacuum chamber. So I went down, I was upstairs then, went down to the welding lab, and I did the same thing. I just did it in there, and I just took a gas tungsten arc and I just melted it with the gas tungsten arc, and they all balled up. And I only got about 50% yield because the gas tungsten arc kind of blew the balls around, and some of them would join together and get too big and stuff. It didn't matter. You could do everything in about 2 minutes rather than 2 hours. So I turned it over to a graduate student and have him make 10,000 balls and gave the guy his balls. There was another time that over here at Draper Lab, they were doing some sort of fancy gyroscope for some missile, and they needed iridium balls. Iridium melts around 3000 C, and they were being charged $1 a piece for these little 10 mil balls. Very spherical, but they were being charged a small fortune for them. I mean, even though iridium's like platinum, when it's a ball that small, the volume is so small that there was like 3 cents worth of iridium in these balls, and they were charging them $1 a piece for it. And so they needed a bunch of them, and they gave me a small research contract, and we basically built a drop tower. In the drop tower, we had to make it out of graphite, and it had to go to about 4,000 degrees centigrade. But by just resistive heating, but you can get that in graphite in a vacuum. And you drop the ball, the little piece of iridium, through the furnace, and it would melt up, and just by gravity, and it would drop by gravity, but just without contacting anything, it would melt, and then it would fall out of the hot zone, and it would solidify by radiation cooling. And so we made them that way. It turns out in in the Civil War, the Army knew that people used to make lead shot by taking, a stream of lead and spraying it. They get nice spherical shot. And they decided they were going to make cannonballs over here at Watertown Arsenal by making a big drop tower. Well, they didn't understand back in the Civil War heat flow very well. And they didn't realize when you get to a cannonball size piece of cast iron or whatever, that it takes a while for it to cool, longer than it takes to drop. And they also didn't understand that, well, you couldn't do it by gravity if it was gravity, so it had to be weightless. So you would have had to have a very tall drop tower, probably a couple 100 miles tall or something, in order to cool this whole thing. So it was an unsuccessful research project because they didn't know how to go through the bond number. But they did try it in the Civil War to make cannonballs by surface tension. And if you could drop it from space to Earth, it should work. Just kind of hard to